Welcome everybody, and I hope you're all keeping safe and sane during the lockdown. Most of us in the UK, well, all of us in the UK are still under lockdowns. I know in other places in the world, around the world, things are getting better. So I'll get right to it. The way today's talk is going to go is we're going to have a brief introduction on what is biochemical engineering. I tried to make this part a bit interactive, so I will be asking you to type in answers to some very simple questions that we'll be asking throughout, and they'll go on to talk about UCL and the department, and then obviously we'll go in quite some detail through the structure of the MSc Biochemical Engineering, and we'll close up with a Q&A section where you can ask whatever you like. Right, so biochemical engineers apply the principles of biology, chemistry, and engineering to produce useful products. This could be things like biopharmaceuticals, biofuels, biopolymers, or industrial use enzymes. Now, in and of itself, to someone that's not really familiar with exactly what biochemical engineering can be, this might not really mean a lot. So what I like to do is I like to draw some comparisons between some other engineering disciplines and how they relate to, or draw an analogy between them and biochemical engineering. So every engineering discipline, if you think about it, has really been developed based on trying to address a particular human need. So in this particular picture that we're seeing here, can anyone figure out what the need is that's being depicted here? So this is a picture of a hut, if it's not clear through your screens. So can anyone let us know what this picture might be? If you could type it in chat, what is the fundamental human need that's being addressed? Right. So it is the need for shelter, right? So we need to have a roof over our heads, and we need to, protect ourselves from the elements and so on and so forth. So there is a design phase where we sort of draw on a piece of paper. Nowadays, it's no longer on a piece of paper; it's all done with computers. But we draw our design. We decide how long the walls should be, how tall they should be, how thick they should be, where will the windows be, where will the stairs be, and so on and so forth. We then have a manufacturing step where we actually construct the design. So we transfer the design from a theoretical concept into an actual of is meant to describe civil or structural engineering, right? Similarly, if I bring up the second set of pictures, can anyone guess what engineering discipline I'm trying to describe there? You can type your answers in chat. It is mechanical engineering indeed, right? So there is the need for us to transport ourselves and to transport goods around the world. Similarly, we do have a design phase where we design where the various bits and pieces that make up a car or a plane or whatever need to go, and what their functionality and property should be. We have a manufacturing step, which is in a slightly smaller scale, and then we have the final product, which will be some form of transportation. So coming back to biochemical engineering, one of the main needs that biochemical engineering is trying to address is, unfortunately, as human beings, we do get sick, and we have the need for medicine and pharmaceutical substances that allow us to overcome illnesses. Much in the same way as other engineering disciplines, we do have a design step where we essentially map out the process of starting from our raw materials or from a particular cell type that produces the drug substance of interest, and how we will convert those raw materials into a final vial, or it could be a pill, or whatever form the pharmaceutical substance will be packaged in. So it's similar to civil and mechanical engineering in that we map out in detail all the steps of how do I go from my raw materials to a final product. Again, we have a manufacturing step, again, smaller scale, and we have the final product, which will be some form of pharmaceutical. Obviously, biochemical engineering is not all about pharmaceutics, but I'm using this as an example of the main, let's say, one of the main classes of products that we associate ourselves with. Now, the main difference with biochemical engineering, obviously, is that the design step is quite different. This is a unique trait that's shared between chemical and biochemical engineering. And the fact is that we need to take into account during our design phase that the properties of the materials we're handling are not constant over time, right? So if I'm thinking about a bolt or a nut or a brick or concrete even, over a considerable amount of time, let's say 50 to 100 years, their properties remain fairly constant, right? If I think about, starting from a cell culture with a small number of cells and a fresh culture media with a particular concentration of nutrients inside it, as the culture progresses, the properties and the concentrations inside that mixture will change, right? So the properties of my materials and the properties of the liquids that I'm handling change constantly over time. And this is something we need to account for during our process, during our design step. Now, let's try to come up through a more, let's say, practical example. Again, focusing on the main class of products associated with biochemical engineering, which is the pharmaceutical industry. So let's say, what is the role of biochemical engineers, right? So it all starts from the discovery phase, okay? This could be a particular, so let's say a biologist or a geneticist or someone from the life sciences discovers a particular organism that produces a very valuable product. This will usually happen in the Petri dish scale, which is, if you haven't seen a Petri dish, it's these small little round plastic discs. They're usually about, I want to say, maybe 5 centimeters in diameter. And they're in very small volume. Usually their capacity is lower than 3 milliliters. They're static. That means there's no agitation of the culture. It all just lays undisturbed. You can't achieve very high cell numbers. The culture time is fairly short, and generally the conditions are suboptimal. But that is often where discovery happens. That is where we discover new cells, new types of cells that produce all sorts of products, and that is where we first start culturing engineered cells, where we try to express a new product of interest. Now, this is where the biochemical engineer comes in, right? What we want to do is we want to take this process, this particular cell that produces the product of interest, and scale it up so that it can satisfy global demand. Now, you can imagine that using Petri dishes, you can't possibly imagine to produce enough quantity to satisfy global demand for things like a vaccine, right? So we need to replicate the culture conditions in a much larger scale, while ensuring that the product we are producing is of the same exact quality as that we identified during the discovery process. So that brings us through a stepwise procedures, and that is what biochemical engineers are tasked with doing. How do we make that transfer? How do we design the appropriate steps? And how do we translate those conditions to those culture conditions to cultures often at a different scale and often under different modes of agitation and so on and so forth. So we start with a lab and pilot scale. This is usually between 5 milliliters to 50 liters. This can be static, shaken, or stirred, depending on the product that we're trying to produce. We'll start having some limited control over the culture environment, such as temperature control. There will be some preliminary process optimization, things like what should my media composition look like? and so on. But we will still be working under some nutrient and mass transfer limitations. So we perform the bulk of process development or early process development, I would say, at this stage. And ultimately what we want to do is we want to reach industrial scale. So now we're talking anything between 20 to 10,000 liters. These are fully controlled, steered, and aerated reactors. We can achieve very high cell numbers in these vessels. However, we start having other issues such as hydrodynamic stress. So for example, the reactor that you see depicted here in this picture is approximately 3 meters tall. So you can imagine cells at the bottom of the reactor experience are being crushed effectively by the weight of all the liquid that's above them. What we need to do, or what we are tasked with doing as biochemical engineers, is making sure that starting from the petri dish, from this very simple type of culture, how can we replicate the exact same well, not the exact same process, but how can we produce the exact same product at a much larger scale and under completely different culture conditions. Now, what we have just been talking about is just a small fraction of what the production of any product using cells or their components involves, right? We've only really dealt with cell culture, denoted by the orange, or defined by the orange box here. In essence, we have many, many more steps downstream of the fermentation. So we have purification, which will involve centrifugation and chromatography, formulation, and finally fill finish until we have the final product, right? So it really comes as no surprise that the development timeline of a new drug from discovery to it being on the shelf is usually between 7 to 12 years, depending on the number and type of clinical trials it has to go through. And what we're trying to do as biochemical engineers is essentially expedite this process from discovery to at least preclinical manufacturing. And what we're trying to do is we're trying to increase productivity throughout, reduce the costs and development time, which is very, very significant, the reduction in development time. So questions that we typically work on trying to identify good answers to is, how will I make it? What will be the sequence of operations that will take place? You know, fermentation is pretty much a given, but particularly downstream, do I need to do centrifugation, filtration? Do I need to break the cells open if the product is produced intracellularly, and so on and so forth? How much can we make? So how far can we push our process through process optimization? How much raw materials will I need and consumables, and how will I source them and how will I store them? So this has to do with process scheduling. How can I ensure that product safety? How can I ensure product safety and that I meet regulatory requirements? If we're talking about substances that are intended for use in humans, we are the required purities are above 99.5%. So we need to take extra caution when designing and developing those type of processes. And obviously, how much will it cost to produce it, and will it be a financially sustainable process? Just briefly, some of the challenges that biochemical engineers have been associated with or have tried or are working towards addressing is obviously very relevant to the times we're currently experiencing, is the response to epidemic pandemics, right? So undoubtedly you will have heard in the news that it will, when this whole thing started, it would take us roughly 12 to 18 months to manufacture a vaccine. And the key challenge there, or the key word there, is actually manufacture, right? It's not that it will take us 12 to 18 months to discover a vaccine, to develop a vaccine that would be effective against COVID-19. It's that taking that product and taking it through this process that I've just described is what will take 12 to 18 months, including the time required for clinical trials. And obviously this is much expedited process because it's in the global interest effectively, right? So things that engineers have been doing is trying to develop this concept of platform technologies, right? So think of it as you have a chassis bioprocess where you have a particular cell type, and all the unit operations are very much defined and somewhat optimized. And you just take the genetic information of the new molecule you're trying to produce, express it in your cellular chassis, and then you've already sped up this whole idea of early process development quite a bit, because it's sort of the process is there. You're just kind of plugging in. It's not as simple as I'm making it sound, but that's the concept behind it. Um, and things like process intensification and continuous processing, which allows us to reach higher yields in smaller volumes. Therefore, we can respond to increases in demand quite rapidly. The other challenge is to reduce the cost of medicine and make it more affordable. The main thing there is, if we can reduce the drug development timeline, let's say cut it from the average 10 years now to, let's say, 7 or 6 years, that will have a massive impact on the cost. The reason for that is roughly 10% or less of the substances identified in the lab, in the discovery phase, ever make it to the market. Most of them fail at various phases through these 10 years. This could be in preclinical or toxicology studies. It could be in phase 1 clinical, phase 2 clinical. It's spread out throughout the development timeline. Now, the cost of those unsuccessful clinical trials and unsuccessful drug development is baked into the drugs that successfully make it to market, right? So by significantly reducing this timeline, essentially, it will cost less to try out new drugs and new ideas. So that should bring the cost of medicine down substantially. Now, in other areas, we have a lot of challenges related to the scarcity of energy and resources. We know we're still majorly relying on fossil fuels. Definitely in Europe, there is a huge push to move towards renewable sources of energy. And where biochemical engineers are involved is in two main areas. It's one area is what's called as biomass valorization or biorefining. So the concept of nothing goes to waste, where you use everything from your everyday life and try to make something useful out of it. So these are ideas like using the used coffee beans from coffee shops to ferment them and produce something valuable, such as bioethanol, for example, or taking agricultural waste. So the residues from sugar beet pulp and producing ethanol out of that as well. And the final challenge is how to develop environmentally friendly processes. So there are types of both natural and human made contamination. Think of a body of water next to a mine. Next to mining operations, this will be contaminated usually in sulfuric and nitric components, and very rich in minerals and potentially heavy metals, and therefore poisonous. Uh, so what you can do is there are particular types of microorganisms that people discover around the world or genetically modify that can sort of eat up that contamination. We call it this biodegrading the contaminants, or the entire process. We call it bioremediation, right? So we're trying to develop these types of processes as well. Now, I'm sure, just to preempt the question that all of you will have, or many of you might have, is what has UCL's and maybe a bit more specifically, what has the department's contribution towards the efforts made to combat COVID-19 be? So what we have done is through the Future Vaccines Manufacturing Research Hub. So this is a big collaboration across many universities. This is led by the University of Oxford and Professor Sarah Gilbert, which is what you read in the news about the Oxford group that's trying to develop the vaccine. That is the group led by Professor Sarah Gilbert, and on our side, on the department of from the UCL side, it's led by Professor Martina Micheletti, who's a professor in the department. What we have done is we have rerouted a significant amount of the funds available to the Vax Hub towards the efforts led by Oxford currently. And what we're currently doing is we're trying to assist them in process scale up and process intensification efforts, as well as to help them develop their downstream processing operations and some product characterization using mass spectroscopy. And finally, we're doing some economic analysis and trying to understand the financial implications behind the manufacture of this vaccine at large scale. So moving on to what's it like to study at UCL. For those of you not from London, this is a map of central London, and this orange box defines the central campus of UCL. It really extends a few blocks around that, but I'd say the heart of the campus is defined by the box I've drew. And you'll start seeing pictures popping up of various famous sites in and around London. So just a few examples. You have Madame Tussauds here, you have the London Zoo up here. King's Cross is a 5-10 minute walk, well, I should say 10-minute walk away. So you really see that our campus is really in the heart of London. It's a really central location. As far as UCL's history goes, it was founded in 1826, and it was the first university to admit students regardless of class, race, or religion. Now, back then, you had to be white, male, upper class to be able to be allowed to have a university education, and UCL broke that mold and was the first university to admit students based on academic merit, irrespective of class, race, sex, or religion. 29 people who were students or academics at UCL have been awarded with a Nobel Prize throughout its history. So it's quite rich. It has a quite rich history in academic excellence. And here you can see a picture. I'm not sure exactly when this picture has been taken from. I'm assuming early 1900s, of the main building on campus and the portico on top, which is still there today. And you can see it in the more modern picture on this slide. Now, today, UCL is consistently one amongst the top 10 universities worldwide, irrespective of which ranking table or list you want to follow, consistently in the top 10. And it has 36,000 students, roughly half of them are undergraduates and the rest are postgraduate students, a fairly equal split between men and women. And we have students from over 150 countries. So that's staying true to our motto, which is London's Global University. Now, one of the benefits of joining a big university like UCL is that you get access to a lot of centralized facilities. And I'll just briefly go through some of the examples. So we have a very well-equipped library with over 2 million books, and an increasing number of those books are becoming available online for UCL students as well. We have several dedicated spaces for students only. So we have the second picture on the left is our new student center. This opened its doors in February 2019, so just over a year ago. It's literally adjacent to the Department of Biochemical Engineering. And it's a 5 or 6 story building that's dedicated solely to students. So it has quiet study spaces. It has religious spaces for praying and meditation. It has recreational areas. It has small rooms for group meetings, for project work, anything you can imagine, basically. But apart from this main student center, We have another smaller building that's dedicated only to postgraduate engineering students. And we have another even smaller hub, again, dedicated to postgraduate students. We have computer cluster rooms spread throughout the campus. So you don't need to carry your laptop with you every day. You can just go and work through in one of the computer cluster rooms, and through the desktop at UCL service. You don't need to be carrying thumb drives and transferring your stuff everywhere. It's all stored in the cloud, and you can access it from any computer on campus, basically. We have a language center if you want to learn a new language or improve your English if it's not your native language. We have a couple of museums and art collections on campus that are open to the general public as well. A full-fledged theater. Again, this is next to the student center, so maybe a 2-minute walk from the department. And on top of the theater, we have the gym. So this is a well-equipped, fully functional gym. Now, apart from, let's say, built infrastructure, there are a lot of student-oriented activities that are offered by UCL, the most important of which is probably careers at UCL. So this is a dedicated department with experts with HR experts and people that can advise you on how to build your CV, how to present yourself for an interview. They organize mock interviews, and they can give you information that's both generic but also sector specific. They organize a number of career fairs throughout the year. Again, these career fairs can be general interest career fairs or sector specific, let's say only engineering career fairs. And they hold a number of workshops that can help you improve your skills and your performance in interviews. We also have a dedicated service for accommodation. They can help you find both student accommodation, so student halls of residence type of accommodation, or even private accommodation if you wish to stay outside the halls of residence. We have a web portal dedicated to new students. When I was new at UCL, I used this portal a lot. It goes from very simple checklists on what do you need to do in order to enroll, application through to enrollment, life in London, how the banks work, how do you open a bank account, how to use public transport, everything that you would need to survive during your first week in London if you're not from the UK. Finally, we have the Student Support and Wellbeing team. This is an excellent team. I've interacted with them quite a lot, and they're there to help you throughout your studies. And you have a couple of deadlines approaching and you're feeling some stress, or it's close to exam season and you're getting a bit overwhelmed, or things happen, knock on wood, or family issues, or you need someone to talk to. Student support and well-being services are there for you, and they're very, very helpful and very, very good at what they do. And finally, we have the Student Union, which is completely independent. This is student-led. It doesn't even have a UCL-based website. They have their own independent website, and they're responsible for organizing all the societies and social events that happen on campus throughout the year. And there are clubs and societies for anything you can imagine: sports, theater, politics, religion, cultural, anything you can imagine. There's most definitely a society for. Okay, now moving into the Department of Biochemical Engineering. This is all of us. These are all the academics and teaching fellows. I've managed to fit them in a single slide. So our info or unofficial motto is that we're a small and friendly department, and if you join us, you join for life. And by that we mean, because the student to staff ratio is excellent, so for the MSc it's roughly one member of staff per 1.5 students, so that's an excellent student to staff ratio. And so we get to meet you, and you get to meet us quite well and quite intimately, and therefore we sort of maintain excellent relationship with our alumni for many years to come. And in fact, a lot of our alumni are involved in our teaching activities in one form or another that we'll discuss in a while. Now, the department itself was the first department to dedicate itself solely to biochemical engineering, to the discipline of biochemical engineering. Before that, most biochemical engineering related activities were run of chemical engineering departments. So this was the first department in the UK to dedicate itself solely to biochemical engineering, and we have a track record of excellence in research, teaching, and enterprise as well. So we had 3 successful spin-out companies originating from the department, one of which was bought a year and a half ago by GSK for an undisclosed amount of money, but it was a substantial amount of money. Now, one of the unique characteristics of the department is that we work extensively with industry, and these are not just logos that I put on a slide that do not have meaning. These are the companies that we have very frequent interactions with. This could be either through collaborative research projects that we run, or it could be that they are involved in our teaching activities. Now, how this is beneficial for you is that well, there are many reasons why. First of all, we have multiple ad hoc recruitment events happening throughout the year. So basically what happens is one of our collaborators comes to us and says, well, we've opened recruitment and we need to fill in a number of positions. Can I come over and have a chat with your students? And it really depends. That's why I say it's ad hoc. Sometimes they just give a presentation and advertise the position. Other times they even hold interviews on site with students, with interested students. The other mechanism is that scientists from these companies participate in our MBI training activities. I'll talk a bit more about later, but essentially these are intensive 4 to 5 day workshops that you as MSc students will attend a part of, and the person sitting next to you as a student for that day might be one of the scientists from one of these companies. And that allows you to start building your professional network in an informal setting. So, during a coffee break, you can go up to them and say, oh, how did you find your job in XYZ company? What were they looking for? How did you present your CV? And slowly start, collecting information of that nature. Now, just to give you an idea, for those of you that will get to do a research project during the summer, our research activities cover a wide range of areas. We go all the way from synthetic biology, so engineering cells, to early process development, to actual whole end-to-end bioprocess modeling and scale-up. And this is a representative selection of a representative selection of research projects that we have given over the past 4 years. So you can see they range from upstream process optimization to CAR-T, scale up, engineering, E. coli, microfluidics, all sorts of things. So a wide variety of research areas available. Okay, now on to the MSc itself. The MSc has 3 routes. One for scientists. This is for students with a background in science or or one of the life sciences. So things like chemistry, biochemistry, biology, molecular biology, and so on. We have one route that is dedicated to engineers. This would include primarily chemical engineers, maybe mechanical engineers, and the like. And then we have the final route, which is dedicated for biochemical engineers. So these are people with undergraduate degree in biochemical engineering or biotechnology. It kind of varies around the world what the suitable degree would be called. Now, if your undergraduate background is not listed here or on the indicative list of topics we list on our website, do not worry. Just send me an email. And I'll go through your transcript and let you know if you would be eligible to apply or not. Our entry requirement is a minimum second-class UK bachelor's degree or international equivalent. Again, there is a link on our website to the international students website, UCL website, where essentially there is a conversion tool. So you enter your country of origin or the country where you obtain your undergraduate degree from, and it tells you what the equivalent grade would be. Now, I have to mention that entry onto our MSc is competitive. So even though technically the minimum would be a second class, usually successful applicants hold a 2-1 or above. If you're not native or if you haven't done your degree in a country where the primary language is English, we would need some proof of your English language proficiency. So this could be an IELTS or a TOEFL. There's a whole list of tests that are accepted by UCL. And then the others is quite straightforward, right? So we need your transcripts, a statement explaining why you want to study biochemical engineering, and 2 references. The deadline for applications this year is the 31st of July 2020. If you are from overseas, I would recommend that you apply as soon as possible to give you enough time to go through your visa application as well. Okay, now, so in terms of the routes, sorry, I'll just briefly go over them. So we start with the route for scientists. We have 4 compulsory modules in term 1. The aim here is we want to take you from graduate scientists and start rejigging your brain and training you in the fundamentals of engineering. So you'll learn things like fluid flow and mixing, bioprocess synthesis, so what are the various pieces of equipment that make up a bioprocess, downstream processing and reactor design. In term 2, again, we go a bit deeper into the fundamentals of engineering. So we do things like heat and mass transfer and bioprocess validation, and we also have the practical component about biochemical engineering laboratory module, where you do end-to-end, you cover all the various steps in a typical bioprocess. Not just the fermentation, but the various downstream purification steps. And finally, in term 3, you undertake a dissertation on bioprocess design. So in order to become a chartered engineer, one of the major boxes you need to tick is you need to have undertaken what is known as a capstone design project. So this is what you get to do in term 3. Now in term 2, you have an optional module, so you can select one of the following 3 modules, so commercialization and an enterprise essentially, sustainable bioprocess and biorefineries, and advanced safety and loss prevention. Moving on to the engineers, in term 1, now the aim here is you're a trained engineer. We want to slightly rejig your mind to start taking into account the nuances from working with cells, which are much more delicate in nature. And let's say, for example, you're a chemical engineering, you'd be familiar with high pressure, high temperature type of reactions. We work in a much more limited range of pressures and temperatures and so on. We'll also give you a background on biology or a refresher on biology if you already have a background there. And then term 2, you'll get to do sustainable bioprocess and biorefineries, bioprocess systems engineering. This has a bit to do with scheduling and the laboratory module as well. In term 3, you get to do a research project as well. So this is a traditional research project that you would expect. Now, both in term 1 and term 2, you get to pick one optional module out of the 3 available in either term. So you can see the options here. Term 1, vaccine, synthetic biology, and microfluidics. And term 2, commercialization, validation, and energy systems and sustainability. And I'll just briefly go through the biochemical engineering route. I'm guessing we probably don't have anyone that would be interested in this in online right now. But basically, term 1 is vaccine. So the aim here is to go in depth. So you have a background in biochemical engineering, you know the fundamentals, and the aim here is to provide depth and breadth of the discipline. So you do vaccine, synthetic biology, and microfluidics in term 1, and then term 2 and term 3 are identical to the engineering route. And you have some optional modules in term 1 and term 2 as well. Right, so to summarize and finish off, what are the unique opportunities throughout the year you'll be with us? The first one is that you get to attend the MBI. These are the intensive 4-day workshops that I mentioned earlier on. Now, these have been developed as a request, in response to a request from our industrial partners who wish to have a training mechanism and an upskilling mechanism for their employees, right? So these are people, trained scientists, trained engineers with several years of industrial experience that need to get up to speed with the latest developments in a particular area, or need to retrain in a particular area. So you get access to that. This is state of the art. This is material that does not exist in textbooks. It's literally the latest development. So not only that, but you also get to interact in an informal setting on an equal playing field, if you wish, with people working in one of the various companies that I mentioned before. Our laboratory practicals are uniquely designed to make use of the pilot plant facility that we have in the department. So this is full end-to-end pilot plant facility. So you get to see not only the layout of how an actual manufacturing site would be organized, but also equipment in representative scales. Our laboratories are very well equipped, so you will be trained on the newest pieces of kit that you would expect to find in industry, and not outdated, antiques in terms of equipment. And then finally, either through guest lectures or a number of ad hoc events that we organize throughout the year, you'll manage to get very good exposure to industry, and that will help you start building your professional network. Now, in terms of graduate jobs, the majority of our students go on to work for the wider pharma sector. This can be either in a research and development role or in manufacturing. This makes up roughly 50% plus or minus of our graduates. A smaller percentage goes on to work in biochemical engineering or general engineering consultancy roles. And obviously, being based in London, we do have roughly around 8 to 10% of our graduates go on and work in the city, so in the financial district of London. Roughly a quarter of our graduates go on to further study, so a PhD study, before they move on to their professional role. And that just shows how research intensive our discipline is. And this is just a ballpark. Obviously, things change year on year. We're living through an unprecedented crisis right now, so this will undoubtedly have some impact on the economy. But on average, what we recommend for our graduates to expect is a starting salary of roughly £28,000 per year. Okay, and with this, I'd like to thank you very much for your attention, and I'd like to open the floor for questions. Right, so let's see. It seems to me that there are some questions already in the chat.
Hi, yeah, there's also there's a question in the Q&A which is, can we still enroll in UCL if we haven't already for September 2020? And if there's any flexibility in the entry requirements because of the current situation, i.e. no exams?
Right. So I didn't understand the first part of the question, which was, is there any, what is the procedure for enrollment? Or I didn't quite understand.
Well,
Could you
just to break
repeat
it
that?
down then, somebody's asking if we can still, I guess it's not so much enroll, but you can still apply to UCL. I think
You can definitely apply.
you can
Yeah,
still
yeah.
apply, and then is it until the 20th of August is the deadline?
27. I had it in one of my slides. I don't remember
Yeah,
by heart. That's why I put it on the slide.
yes,
It's the last. I know they've extended it, right? So it's usually the last Friday of July, but for this year, due to the coronavirus situation, they've extended it to the 20th of August.
okay. And then what's the situation as regards flexibility on
Right. So
exam requirements?
the entry requirements have not changed per se. If your university decided not to hold examinations but still awards you the degree, that's what we care about. We don't have any particular requirements on, you know, whether your final year included examinations or not, as long as you're able to graduate normally and provide your degree and your final set of transcripts. Otherwise, the usual entry requirements that I mentioned still apply. Sorry, Kim, for whatever reason, most of the fonts come out really weird. So can you read the questions
Okay,
for
sure
me?
thing.
Because I can't.
Okay,
I make no.
so no problem. So just going back a little bit, somebody did ask about the Oxford vaccine, but I said that we're doing a taster lecture. So I sent a link to that. It's probably more relevant to what's going on there, rather than going to detail.
Right. So I briefly touched upon this during my presentation, but again, just to summarize, in case it wasn't clear or I just went a bit too quickly over it. The main ways in which we're contributing to the efforts from Oxford is in upstream optimization studies on vector production. So that is to help maximize the quantities of vaccine available. Downstream processing optimization, so how to purify the vaccine and some characterization using mass spectroscopy. And finally, some formulation freeze drying work. So this vaccine, or at least a vaccine that is being developed by Oxford, is not available, is not stable above 25 degrees. So in order to distribute it around the world, you either need a formulation that is based on freeze drying, or you need to have a cold supply chain, which is very expensive and complicated to run. So these, I'd say, are the three main areas that we're contributing towards in relation to the Oxford efforts.
Great. And somebody else was asking, as someone who graduated 4 to 5 years ago, does the university need an academic reference as part of the application process, or can they have a professional reference instead?
So for people that have graduated a while back, we are a bit more relaxed. My advice would be, if you could get at least one academic reference, that would be great. And you can ask your personal tutor, or you can ask someone you did a research project with, for example. If at least one is from an academic environment, that would be good, yes. But you don't need to do both, definitely.
Great. I've got here as well somebody asking about TOEFL score. Is it all right to have one that's 2 years or 4 years old? Does it have to be up to date?
That would I'll need to check on that. If you Google UCL English language requirements, you'll have detailed instructions there. I believe the grace period is 2 years, but things change, and particularly due to the coronavirus situation, things might be relaxed for this year. So you'll find the most accurate and up-to-date information on the English language requirements website.
Okay, we've got a question here, which is if you've got integrated PhD programs where students undertake MSc coursework modules before they undertake research. I think that perhaps more relatable to the MRes, Alex?
Uh, oh, um, so this MSc, just to make this clear, this MSc is not part of an integrated program. And we do not have an integrated program in the sense that it exists, for example, in the States, where any PhD in engineering at least would involve a 2 years master's followed on by 3 to 4 years of research, and all of this is called a PhD. What we do have for as part of our EngD degree program, so that's an engineering doctorate. It's essentially exactly the same as a PhD. The only difference is it's done in collaboration with an industrial company. So the first year of that EngD degree is an MRes degree. So a master's in research degree, which will include some formal taught elements, not as much as a normal MSc, plus a research project. So that's the closest we get to an integrated PhD slash master's that would resemble the structure in the United States. I'm hoping that's what the question was aimed at.
Great, thank you. There's a question here about whether lab sessions will be deferred to a later term, so term 2 or 3, if the COVID-19 doesn't allow reopening.
So we've been very lucky with this because we revamped our timetabling and the way we do labs, to be honest, starting from 2019, 2020. So this was the first year we ran this revised program, degree program. Or by design, our labs are in term 2. So all of our labs are in term 2. So hopefully that would not create any problems. Having said that, we are making contingency plans of being able to move our labs into term 3 as well.
Great.
If such a thing would be required.
Okay, somebody's asking whether biochemical engineering is working on biofuel research.
Yes, it very much is one of the leading disciplines. Sorry, I should have made this disclaimer. The majority of my examples are around biopharma because that is what most people associate it with. But yes, biofuels is definitely one of the primaries. And in fact, we have at least 5 or 6 academics actively doing research on biofuels, be it with algae or so biodiesel via algae, or second generation biofuels, which usually involve some type of yeast fermentation.
Great, thank you.
And in fact, one of the modules, which is the sustainable biofuels and biorefineries, is around those concepts.
Great. So somebody's asking about how you allocate streams, whether there's a quiz or a test or transcripts.
No. There's no quiz or a test during the application process. All applications end up with me. I go through the transcripts and then I make the allocations based on your academic background. It's not necessarily a matter of choice. It's a matter of which route is your background suitable for, right? So if you have let's say another graduate degree in chemistry, you can't go into the route for engineers because that is designed and delivered assuming a full engineering background, right? Now there are several degrees, I have to say, where, because the way higher education is organized around the world is slightly different, and there are some degrees which could end up in either stream. What I do in those cases is I make my initial allocation before you arrive here. And then during induction week, I make sure to meet with everyone that wants to have a chat on whether they have been allocated in the appropriate stream or not. But I have to say the majority, like 95% of the cases, is very clear cut, as in you're either an engineer or you're not an engineer by in terms of your undergraduate training. So it's fairly clear cut.
Okay, somebody else is asking if there are any funding opportunities from the university for overseas students.
Right. So unfortunately, the department itself does not offer any scholarships. However, If you go onto our website into the FAQ section, the frequently asked questions sections, I have a link for the funding portal of UCL. So that's a tool where you can enter the degree you want to study for, your country of origin, and a bunch of other options, and will provide you all scholarships that you would be eligible to apply for. And this changes throughout the years because obviously scholarship schemes run with different timelines. So it's worth checking every now and then.
Great, thank you. So the next one is, somebody said, I saw a wide variety of engineering courses applicable, but I didn't see more quantitative engineering degrees eligible for application. So example, industrial engineering.
Right, again, as I said, I just have a representative selection of disciplines on my slides. It doesn't mean that if your discipline was not listed, you're not eligible. The best thing to do would be to send me an email with your transcripts. And to be honest, I'm not really interested in the grades at this phase. I'm interested in seeing the full list of modules that you will take during your degree. And I'll be happy to give you an answer based on that before you even apply.
So there was just one question about UCAS applications, which I think I've cleared up directly. From what I see here, there are no more open questions. So if you've got any more questions, could you send them through now? Otherwise, what I have done as well is, Alex, I sent you, because before you joined, I asked everyone what degree they were studying. So I sent that through to you as well. So you've kind of got an idea of the makeup here. It's always really interesting to know what backgrounds people are coming from. Somebody's asking about Alex's email.
I'll type it.
We'll send a follow-up email as well afterwards to everyone. So you'll have contact details, but I'll just pop it in here now for you as well. Just give me a moment.
Yeah, I've typed it in as well. Hopefully you can see what I sent. So it's alex.kiparisides@ucl.ac.uk. In case you can't spell my last name, which is completely understandable, it's on the website as well. Under the MSc. If you go into the MSc website, my contact details will be there as well. And but I've typed it in the chat.
Yeah, so it's in the chat. If you don't have this on your machine afterwards, if you go to our website, there are a variety of means of getting in touch with us. If you just contact anyone, they'll be more than happy to put you through to Alex or myself if it's something I can deal with, or one of the TNL team. We'll always make sure your query gets through to the appropriate person. Okay, I'll just mark that as answered. So if there are any more questions that come in, if anything occurs to you afterwards that you didn't get a chance to ask now, or something you'd like to follow up on, again, by all means, come to me, come to Alex, and we'll be more than happy to talk to you again. Okay. All right, I think that's it.
Thank you very much for attending. If any questions come up later on, just feel free to send me an email. I'll be happy to answer any questions you may have. And apology for the slight delay in getting started.